Hi, in this video we are going to calculate the Laplace transform of the unit step signal u of t and also the signal u of minus t. Okay, so let us carry out the calculations simultaneously so that we will be able to see the details of the calculations. So let x1 of t be u of t. Okay, and we define u of t as follows. The unit step signal is, remember, is 1 for t greater than 0. And let us define the value at t equal to 0 as 1 over 2 and 0 for t less than 0. In fact, the value at t equal to 0 is not important or critical because when you calculate an integral of u of t over any interval containing 0, the value at that single point will have no effect on the integral. And similarly, in the Laplace transform, it will have no effect. But for a certain reason, which will be clear throughout the example, we assume that u of 0 is 1 over 2. And let x2 of t be u of minus t. Okay. Now the Laplace transform of x1 of t is x1 of s. So it is from minus infinity to plus infinity. U of t e to minus st integrated with respect to t. Here s is our complex variable sigma plus j omega, and similarly x2 of s is from minus infinity to plus infinity u of minus t e to minus st integrated with respect to t. Again, s is the complex variable sigma plus j omega. So, this integral x1 of s can be written as an integral from 0 to infinity because u of t is equal to 0 for negative values of t. The value is 1 and we have e to minus st integrated with respect to t. Similarly, for x2 of s, u of minus t is 0 for positive values of t. Therefore, this is from minus infinity to 0. Again, the value is 1, e to minus st integrated with respect to t. Okay. Now, in this integral, we ask the question, okay, how can we claim that this integral is a convergent integral? It exists. Remember, s is the complex variable sigma plus j omega. Now, j omega term has no effect on convergence of the integral because e to minus j omega t is sinusoidal. It is bounded, in other words, its magnitude is equal to 1, and therefore sigma is important. So, this integral is convergent. This integral is convergent, or this integral exists if real part of S, which is equal to sigma, is positive. So we will have a decaying exponential, and at t equal to, when t tends to infinity, e to minus sigma t will tend to 0 if sigma is chosen to be positive. Okay, now what about this integral? In x2 of s, we have an integral from minus infinity to 0 of 1 e to minus st integrated with respect to t. So this integral is convergent. Remember, exists means convergent, is convergent because we have a limiting operation as in the limit as t tends to minus infinity, the lower limit of the integral. If real part of s is now positive, real part of s is negative now in this case, because if real part of s is negative, then the exponent will have a positive exponent, e to sigma t. E to minus sigma t will, minus sigma will be positive, in other words. So as t tends to minus infinity, this integral will be convergent. The integral from minus infinity to 0 corresponding to this Laplace transform calculation will be a convergent integral if real part of s, and real part of s is sigma, if sigma is negative. So under this condition, x1 of s will be equal to minus 1 over s e to minus st evaluated at 0 and infinity. At t, as t tends to infinity, e to minus sigma t will tend to 0 because sigma is positive. So the limit at when t tends to infinity will be 0. So we have 1 over s. So x1 of s is 1 over s. Therefore, the Laplace transform of u of t is 1 over s. And now let us look at x2 of s. x2 of s is equal to, again, minus 1 over s, evaluated at the integration limits 0 and minus infinity. Sorry, we have also e to minus st, and the integration limits are 0 and infinity. As t tends to minus infinity, e to minus sigma t will tend to 0 because sigma is now negative. Okay. And the integral, the result of the integral will be minus 1 over s. So Laplace transform of u of minus t is minus 1 over s. However, in the Laplace transform, remember, the region of convergence must also be specified. That means the subset of the S-plane over which the Laplace transform exists. So here our region of convergence for x1 of S, let us call it ROC1. It is all those S such that real part of S or sigma is greater than 0. And here ROC2, the region of convergence of x2 of S is all those S such that real part of S is negative. In other words, here if we plot the region of convergence, okay, this is sigma and this is j omega and this is our S-plane. So sigma greater than 0 is this half plane, and over here our region of convergence is sigma less than 0, sigma j omega, and this is our region of convergence. So this is the region of convergence for x1 of S, and this is the region of convergence for x2 of S. Okay, so this is the calculation of the Laplace transforms of u of t and u of minus t. Now, we ask the following question. This question is interesting and important. Now, note that x1 of t plus x2 of t is 1. So let us call this our new signal x of t. So when we add x1 of t, u of t, and x2 of t, u of minus t, for all t, we have the constant value 1. This is our new signal x of t. So the question is, what is Laplace transform of x of t? The constant signal, in other words, the DC signal. Okay. Now, can we do the following? Can we add x1 of S and x2 of S and claim that we obtain the Laplace transform of the sum of x1 of t and x2 of t? Okay, we cannot do that because x1 of S has the region of convergence specified as the subset of the S-plane, satisfying the condition real part of S greater than 0. And the other signal, x2 of t, has the Laplace transform x2 of S, where the region of convergence is now all those S such that real part of S is negative. So the intersection of the two convergence regions is the empty set. Okay? So the answer to this question is the following. X of S does not exist. Okay? So the Laplace transform of the signal, which is equal to 1 for all t, the constant signal, does not exist. Okay, thanks for watching.